Alright, so we're going to introduce circuits. The first thing is a new term. It's electromotive force. It's abbreviated EMF, and it's any type of device that is able to move the charges through a conductor. The symbol is a script E, and it really is the same thing as a potential difference in terms of the math in the circuit. So it's the work per unit charge. We have both an ideal EMF and a real EMF. A real EMF is a battery, so as current flows through the battery, there is some resistance through that device. So when the battery is not connected, the EMF is equal to the potential difference. So the battery looks like it does in the circuit. But if it has current moving through it, the EMF is going to be greater than the potential difference across the battery, because inside of the battery it acts like it has a resistor. We're going to apply the loop rule. Which is the algebraic sum of the changes in potential through any complete loop must be 0. And we applied this last year. So here's our circuit. All right, let's look at this circuit here. We have a battery and the EMF, little resistor R, and big R. And let's look at what's happening in this circuit graphically before applying the loop rule mathematically. All right, so what we're going to do is we're going to make 2 points. This is point A, and this is point B. Let's reference those. And as we move through the circuit from point A, so that would be point A, we're going to hit that EMF device, and that's going to raise our potential, travel through the wire, and it's going to be constant. And then we're going to hit that resistor, which is going to drop the potential, travel through the wire, and then we're going to hit the other resistor, and that's going to drop us all the way back down to the original voltage, and then back to point A. So this bottom axis will be the path through the circuit. So right at this point would be the one terminal, and by the time we make it through, we've got to the other terminal, and we have a wire because everything stays constant. Here's resistor little r, there's a wire, then we hit resistor capital R, and then we're back to the wire. This value here is the value of the EMF. This value here would be the voltage across the battery. So if I put a voltmeter on each end of the battery, as there's current flowing through it, it would read less than the EMF because of the internal resistance. And again, here's the rise between the terminals. Here's the drop over the resistor, and there's the drop over the last resistor. And this is that drop value. So how much that falls is the current times the little resistor. However much this falls is that IR. All right, so we're gonna write out the loop rule for this. Move this away. Okay, as we move from A to A, we're going to go through the battery, and we're going to gain potential equal to the EMF. And then we're going to lose potential equal to the current times the internal resistance. Then we're going to lose the rest of it through the other resistor, and that's going to equal 0. That's just moving through the circuit this way as our loop. Let's move this over. We can see the I can be factored out, and here you'll have the sum of the two resistors, and this is the equivalent resistance for series resistors. And the equivalent is just the sum of however many resistors we have. In this type of circuit, if it's a series circuit, the I is constant. So it's the same throughout the entire loop. And then the voltages will add up so that the voltage drops across each resistor will add up to be the EMF. Now, just to relate this to a circuit that doesn't have internal resistance, I'm going to go from here, and I'm going to just move the one potential over to the other side. And this value right here is going to be the reading, because it's the total drop. It's the gain across this battery voltage EMF source and the drop through that resistor, so that the voltage reading that I'm reading across the terminal is what this is. So this is basically the V that will be read across the battery. And here you can see it's just Ohm's law. It would act just like a circuit without any internal resistance for a single resistor. And instead of calling this the EMF value, you would call it the voltage value. Now we're going to look at how to find the potential difference within the loop. Instead of going through a complete loop, we can go between just points A and point B. All right, so here's a circuit, and we want to figure out what the potential difference between A and B is. So we want to figure out potential difference between A and B. So to do this, we're going to start at point A, and at point A there should be a certain potential. So that'll be the potential at A. Then as we cross the battery, we're going to add the EMF. This still is the EMF. We're going to subtract the voltage drop through that internal resistor, and then we'll have the voltage at point B. So all we did is just move just a part of the loop in this circuit. So we can continue around if we were going to use the loop rule back to the beginning, but we're only moving through the circuit between A and B. All right, so we move this around so that we get the potential difference. So we're going to have right. So now we have the difference between those 2 points, which is basically take the EMF minus the drop, and what we can really see here is what I've stated before, that if we put a voltmeter on each side of the battery, we would get the voltage reading. So this is really the voltage of the battery. All right. Now we can go the other way. We can go from A to B following this path. So we would do the same thing. We would have the voltage at A minus the drop through this resistor, and that's going to equal the voltage at B. Oops, made a mistake here. So the current in this circuit is going from the positive to the negative. So the current is actually moving this way through the circuit. So since the current is moving down, but our loop is going up, this becomes plus. As we work across the resistor, it becomes plus. So that VI times R is equal to VB minus VA, which again is that voltage across the battery, where you get the Ohm's law equation again. If we compare these two equations, we know that here the potential difference is equal to V, and here the V is equal to IR. So both potentials are equal to each other, so the EMF minus the internal resistance is equal to I times R. Because each different way basically proved that from A to B this way is the same as A to B the long way.